Hello everyone, let's take a look at this problem involving Newton's laws, specifically on static equilibrium. In this problem, they're saying consider a 52 kilogram mountain climber shown below, and the first part of the problem is to find the tension in the rope and the force that the mountain climber must exert with her feet on the vertical face to remain stationary. It says assume that the force is exerted parallel to her legs. Also assume a negligible force exerted by her arms. We'll get to part B later on. Let's focus on part A. As you probably know, a good place to start is with a free body diagram. But before we do that, let's explore why this is a static equilibrium problem. What in the problem gives you a hint that this is a static equilibrium problem, and that's the remain stationary part. And that's what you want to kind of jot down. Right, so that's the key word that gives you a hint that this has to do with her being stationary, thus is a static equilibrium problem. So it is a Newton's laws problem. A good place to start always is to say, okay, we know that we're going to sum all the forces, and that has to equal mass times acceleration. And you should know that even though we write F equals ma like this, it's a vector equation, meaning kind of deceptively it's hiding three different equations inside, right? So when you write F equals ma, what we really mean is we want to sum forces in the x direction, set that equal to the mass times the acceleration in the x direction, sum the forces in the y direction, mass times acceleration in the y, sum the forces in the z direction, and mass times acceleration in the z direction. So these three equations are what we write in a compact form by saying F equals ma. So in general, you need all three if you have a three-dimensional problem. But in this particular case, one for one thing, we by the phrase stationary, we know that this is a static equilibrium problem, meaning that there is no acceleration. So the sum of the forces has to equal 0. And in this particular case, as you can see, it's a two-dimensional problem. We don't have to worry about the z component. So we'll sum the forces in the x direction, set it equal to 0. Do the same thing for the y direction, set it equal to 0. Okay, so I'm thinking about the big picture here, right? So when I'm looking at the problem, I'm thinking, okay, I have to apply Newton's laws. What does that mean specifically? Okay, that means sum of the forces is equal to 0, right? So I'm kind of considering the big picture, the big ideas first, and then I get into the details of solving the problem mathematically. So a good place to start with these sorts of problems is to draw yourself a free body diagram. So let's put a coordinate system here. So here's x and y, positive x going to the right, positive y going up. Okay, so let's put the person right in the middle as a dot, right? So a free body diagram doesn't have to be too fancy. A person can be represented by a dot. And the idea with a free body diagram is to put all the forces acting on the object of interest, right? So here we're focused on the mountain climber, and so we're thinking all of the forces acting on her. Now, there is a little trick here in the problem where they're asking for the force exerted by the mountain climber, right? So this is an application of Newton's third law as well. You kind of have to think about that too. When the mountain climber pushes against the wall, then the wall pushes back on the mountain climber. The direction of that force is opposite each other, but the magnitude is the same. If we solve for the force that the wall is exerting on the mountain climber, then we all can also figure out what the mountain climber is exerting on the wall. So it is an application of Newton's third law. Okay, so let's put the tension force. As you can see, there's the tension through the rope at a particular angle. So we're going to draw that tension. And there is an angle that we have, right? So the angle from the wall to the rope is 31 degrees. And you can figure out that this is also 31 degrees. So how do I know that's 31 degrees? If I have a parallel line like this and another parallel line like this, and there is a line that cuts them through like this, then if we know what this angle is, theta, let's say, then we know that this is also theta. So that's what you're doing here, is that you know that that angle up there is 31 degrees, and therefore the angle from the vertical near the mountain climber to the rope is also 31 degrees. So this angle is 31 degrees. Now, the other force we have to put in is the force by the wall on the mountain climber, right? We want external forces to the object of interest here. What we're focused on is the person. So all forces acting on the person need to be put on the free body diagram. So we have that force. I'll call it FL for force on her legs from the wall. And again, we can figure out this angle. This is 15 degrees. How do I figure that out? Well, similar thing as before. If you have two parallel lines and you have a line that cuts across like this, and that's what's happening here, right? So we know if you draw a line perpendicular to the wall, and from that line to the legs is 15 degrees. So we know that this angle, let's call it phi, is equal to this angle, right? So that's why we know that this angle here shown in the free body diagram is also 15 degrees. We have one more force. We have the force on her legs from the wall. We have the tension, right, that's pulling on her because of the rope. And we know there's the force of gravity, right? So the earth itself is pulling down on the mountain climber, and she has a certain weight. Okay, so we have all the forces acting on her. You want to take a moment to look at your free body diagram, make sure there's nothing else missing, no other external force is applied onto her, because if there's a force missing, then your analysis will be incorrect. So you'll have to come back to your free body diagram and go over again. It's worth pausing, take a few seconds to think about your free body diagram, make sure you captured all the forces. It is to your advantage to make sure that that step is correct before you go on and do the algebra. Okay, so now it's an application of Newton's second law, right? So we will sum the forces in the x direction, set it equals 0. We'll sum the forces in the y direction and set it equals 0. Let's go ahead and do that. We're going to sum forces in the x direction. So what are the forces in the x direction? We need to break up the vectors. So each of them treat the vector itself as the hypotenuse of a right triangle, and you need to make two right triangles. So the first one with the tension, the right triangle kind of looks like this, right? And the trick to that is form the other two sides of the right triangle by following along the same direction as the axes, right? So this line right here follows the x-axis, this line right here follows the y-axis, and there's your right triangle. And same thing for FL, treat the vector itself as the hypotenuse, and then you need two sides, and you get the two sides by following your coordinate system. Here's following y, and here's following x, and there's your right triangle. What are the components in the x direction? For tension, we see a negative component in the x direction, so negative tension sine of 31 degrees, right? So the opposite side is involved. It's negative because from the center, you have to go in the negative x direction to get to where the end of the tension vector is. So that's negative. And then we consider FL, that's positive. Notice that FL points to your right and up. Therefore, the x component is positive. So you have FL cosine of 15 degrees is equal to 0. I recommend when you're doing the breaking of the vectors, just do it using trigonometry. Don't worry about if the x component is positive or negative. Just find the side, figure out, okay, the component of tension in the x direction is t sine 31 degrees. Well, you need to figure that out first. Once you know that, then you can figure out, is that a negative or a positive by looking at, from the center of your coordinate system, how do you get to the end of the tension vector? Which direction in x and y do you have to travel, right? So in the case of the x component of tension, you have to go in the negative x direction to get to the end of the vector, right? Do the signs, SIGN signs, after you do your trig. That's kind of my recommendation, because it'll help you kind of not do too many things in one step. Okay, so then what we're going to do is sum the forces in the y direction. We'll do one of the easier ones, the weight, right? So minus the weight, it's in the negative y direction. And then let's put in FL's contribution to the y direction. It's positive FL sine of 15 degrees. And then we have the tension. So that's also a positive tension cosine of 31 degrees, again, equal to 0. You have two equations, and if you look, you have two unknowns. You don't know what FL is, the force on the legs. You don't know what the tension is. You do know what the weight is, right? So you know that weight is equal to m times g. So you're given the mass of the climber. You know acceleration due to gravity on Earth at surface level is 9.8 meters per second squared, right? So the weight is known, but the tension and the force on the leg, it's not known. So we have two unknowns and we have two equations, so that's good. You can solve it, right? So you need as many equations as there are unknowns. If you have two unknowns, you need two equations. If you have three unknowns, you need three equations, right? So we have enough equations to solve this, and there are different ways to solve systems of equations. Go look back and review in your math textbooks, kind of look online if you need a review of different ways to solve systems of equations. You can use a matrix, for instance, right? So there's different ways to do it. The easiest one, not always the most efficient one, but the easiest one is to make a substitution. So we'll take the first equation and just kind of move the terms around a little bit. So I'm going to say FL cosine of 15 degrees is equal to tension sine of 31 degrees. Just switching the terms, moving the negative term to the right-hand side. And then I'm going to solve for FL, right? So what I'm going to do is divide both sides by cosine of 15 degrees. And what I'm left with is FL is equal to tension times sine of 31 degrees divided by cosine of 15 degrees. Okay, so I'm going to use that. What I'm going to do with that is take this and go up to the second equation and plug it into FL in there, right? So if I do that, the second equation will just have one unknown, and that one unknown is tension. I'll show you what I mean. So that second equation, all I'm going to do is rewrite it. So minus the weight plus, I'm supposed to have the force L, right? So the force on the legs. But instead of writing FL, I'm going to substitute this expression we just found for FL. So that's going to be tension times sine of 31 degrees divided by cosine of 15 degrees, right? So that's what FL is, and then I'll multiply by sine of 15 degrees, right? So that was still part of that equation, so I'll keep that there. Continue on to t cosine of 31 degrees is equal to 0. So now what I'll try to do is to isolate t. I'm going to move the weight to the right-hand side. Then I have tension sine of 31 degrees, tangent of 15 degrees, because there's a sine divided by cosine. Sine 15 divided by cosine 15 degrees is tangent of 15 degrees, plus t cosine of 31 degrees is equal to the weight. Move the weight to the right-hand side. If I factor t, then I have sine of 31 degrees times the tangent of 15 degrees plus cosine of 31 degrees is equal to the weight. And now what I'll do is divide, right? So then I have the tension is equal to the weight divided by sine of 31 degrees, tangent of 15 degrees, plus cosine of 31 degrees. So you'll know all these values, so now you can go ahead and put the numbers in. The weight, again, is mass times g, so mass is 52 kilograms, and then g is 9.8 meters per second squared, divided by sine of 31 degrees, tangent of 15 degrees, plus cosine of 31 degrees. When you're putting this into your calculator, make sure your calculator is in degrees. It could be in radians, so check that. Oftentimes, one of the causes of problems is the calculator is in the wrong mode. So just double check, and you should get something like 512.073 newtons. I'm not going to write this in significant figures, the correct significant figures, because I'm going to use that to solve for FL. So it is to your advantage to carry more decimal places than the proper significant figures would indicate. So if you're going to list this as an answer, do your correct significant figures. But we need this number to solve for FL, right? Because we have an expression up here, this one right here, for FL. Once we know the tension, we can go and solve for FL, which is equal to the tension, which is 512.073 newtons, and multiply that by sine 31 degrees divided by cosine of 15 degrees. Should give you something like 273.041 newtons. So you have now the tension, going back to the top here, the tension on this rope, right, is now, you know the number, 512 newtons. And then you also know the force on the legs from the wall onto the person. That is also known. It is now 273 newtons. Notice that if you're going to answer the question, the answer asks for kind of the force that the climber applies to the wall, right? So it's the same magnitude, it's the opposite direction. So the reason why you don't put that force in your free body diagram is because if you're drawing a free body diagram of the person, the force that the person applies onto other objects is called an internal force, right? It's internal to that object. It's not something external acting on the climber, right? So that's why you don't want to list that force, right? The one they're asking for. You're just using Newton's third law to put in the external force, right? The force pairs that are external to the climber. That's what goes in the free body diagram. But at the end of the day, the magnitude is the same, right? It's just that you're now aware the force that the climber applies onto the wall is the same magnitude, 273 newtons, just pointing towards the wall. So we've done part A. They asked us to find the two forces. We've done that part. Now what we have to do is to find the minimum coefficient of friction between her shoes and the cliff. Right? So there's some friction involved here. There was friction to begin with. We didn't directly deal with it. We just treated the force on her legs as just a force. But now we have to get a little bit more detailed. Okay, so let's take a look at this force FL in a little bit more detail. And to help us, let's just redraw just that force. Okay, so this is FL. We know this angle. It's 15 degrees. Let's think about what is really causing this force, right? So we broke the force into components, right? So we said there's a y component and an x component. We made this right triangle. Right, so we did that earlier. We broke the force down into components, but now here's our chance to really think about what is the cause of this force. Okay, so there is a part of this force that is in the same direction as x, right? So there's a part of the force that points like that. There's a part of the force that points upward like this. So let's first think about the one that's going in the same direction as x, right? The one that is horizontal. If we look back at the setup here, right, they say that the rock face is vertical, And when you think about the surface, if you push against the surface, it will push back. If you push against the wall, for instance, right, you go up against the wall and you push against the wall will push you back. That is, the force is going to be perpendicular to the surface, thus the phrase normal force, right? So normal, like the fourth or fifth definition in the dictionary, not like normal like typical, but normal like 90 degrees to the surface. So a normal force acts 90 degrees to the surface. So if you have a surface that's vertical, when you have that and you push against that vertical surface, then the force that the surface pushes on the climber, this normal force, is acting in the direction of x, right? So that component of FL that is in the same direction as x is the normal force, right? Is normal to the surface. But notice that that's not all of it, right? So the reason why there's FL, right? The reason why this climber can kind of do this and stay put, right? There's a force on the climber by the wall, but only some of it is by the normal force, right? The pushing against the surface pushing against the climber, that normal force is only part of the story. There's this vertical part, right? So where you have to think about where the vertical part is coming from, and the vertical part is coming from friction, right? So static friction is what's holding up at least that end of this FL, right? So the vertical part is the force of friction. So let's write that in. So this is F. I'll say F for friction. So this is what's going to help us find this minimum coefficient of friction between her shoes and the cliff, right? So we don't want to use FL, right, the 273 newtons. Think about that as your normal force and try to find your friction that way. That is not what's going on. The friction is only the vertical part of FL. So FL, even though we're writing one force, right, up here, when we're just making our free body diagram, we're saying it's one force. It's really two, right? There are two forces involved. One is the normal force, and that's the component. When you push against the surface, it pushes back on you, normal, 90 degrees to the surface. That's one aspect. And then the other aspect is the friction. So you can kind of think about, well, what if this is really slippery, right? There's ice on the wall. Then maybe the friction is barely there. The frictional force is essentially zero. The wall can still apply a normal force regardless of if there's friction or not. Yes, there could be ice, right? It could be made entirely of ice, right? It could be really, really slippery. But if you have a wall made out of entirely ice and you can push against it, it can still apply a normal force, even though maybe it barely has any ability to produce any frictional force. So in this case, there is friction. Just kind of pay attention. It can be that part B can be a little confusing because you really have to think about what FL really is. Okay, so once we know that, I think it becomes a little bit more straightforward. What you have to do is think about okay, the force of friction is just the vertical part of FL, which is FL sine of 15 degrees. We know that the maximum static friction you can have is the coefficient of static friction times the normal force, right? So that's the maximum value that you can have. So let's assume that's what you're going to get, right? So just what is the value here that you're trying to solve for? So you're going to say the coefficient of static friction times the normal force, and we can say that's equal to mu s, right? Which is what we're trying to solve for. And then the normal force, we know, well, that's the horizontal part. So that's FL cosine of 15 degrees. Let's write that down here. So you say that FL sine of 15 degrees is equal to mu s FL cosine of 15 degrees. So then the FLs will cancel. Mu s is equal to sine of 15 degrees divided by cosine of 15 degrees, which is equal to tangent of 15 degrees. So if you put that in, tangent of 15 degrees, you should get the value for static coefficient of friction to be 0.268. Okay, so we've done both parts of this problem. As you can see, we can do this. It just takes a little bit of work. It takes very carefully drawing a free body diagram, thinking about the big picture. When you're thinking about Newton's laws, what does that mean? Summing up forces. Do we want to set it to ma? Do we set it to 0 in this case because we were told it's stationary, therefore it's a static equilibrium problem. So applying F equals ma in the x direction, the y direction, then it becomes an algebra problem, right, where you have two equations, two unknowns. We solve for the tension, we solve for FL, so that way we have the two forces. And then the second part of the problem is getting a little bit more into, well, what is FL when the wall applies a certain force on the climber? What does that really mean? What are the components of it? Where does that force come from? And you can see that force, even though we can list a certain number to it, it's really coming from two different forces, the normal force and frictional force. Okay, so hopefully that gives you an idea how to do problems like this that may be a little bit more complicated. Make sure you're drawing a free body diagram. Make sure you're summing up the forces like this. Try to do it step by step as clearly as possible. Kind of go very slowly through your algebra. You should be able to solve it that way. So this is what you do for a static equilibrium problem. F equals ma is just sum of the forces is equal to 0, right? So that's one set of problems that you will encounter when you're doing Newton's laws problems. One is static equilibrium problems where the acceleration is 0. There'll be other cases too, right, where there is an acceleration, so more on that later. But hopefully this is helpful.